Okay, picture this. You're on a massive ship, way out in the middle of the ocean, hundreds of miles from the nearest land. It's basically a floating city, a self-sufficient world that has to make everything it needs to survive, and that includes fresh water. So how in the world does a modern ship make sure its most precious resource is always safe? Well, let's dive in.
So our first stop is figuring out how you even get fresh water on the high seas. Because out here, it's not like you can just turn on a tap. You've got to take the endless salt water of the ocean and somehow turn it into water that's pure enough for every single need on board. And it has to be perfect, 24/7.
So yeah, that's really the big question we're tackling today. How does this massive floating island of steel turn the ocean into high-quality fresh water, not just once, but continuously, reliably, and without fail? And you gotta understand, the standards are incredibly high. This water isn't just for the crew to drink. It's used for everything, from cooking and cleaning to becoming feed water for the ship's powerful boilers. It even cools down critical machinery. Each of those jobs needs a specific level of purity, and if you get it wrong, the consequences can be huge.
The solution? It's a system that never ever sleeps. It's a constant, vigilant monitor that's always on the job, testing the water quality to make sure it stays exactly where it needs to be. You can really think of it as a digital watchdog for the ship's most vital resource.
So, what is this digital watchdog? Well, at its core, it's an electronic pH sensor. It's a pretty brilliant piece of tech that translates the invisible chemistry of water into a language that the ship's computers can actually understand.
At the heart of this whole setup is the pH transmitter. Its job sounds simple, but it's absolutely crucial. It measures the water's pH, how acidic or alkaline it is, and it turns that chemical property into a simple electrical signal.
Here's how it works in a nutshell. You have a probe, an electrode, just sitting there in the freshwater line, constantly sensing the pH. The transmitter reads that measurement, and then, this is the clever part, an output circuit converts it into a very specific electrical current, a 4 to 20 milliamp signal. That signal then gets zapped directly to the engine control room.
Now, this 4 to 20 milliamp signal, this is the real secret sauce. We have to decode it to see what's going on. This is pretty much the universal language of industrial sensors, and it's how a chemical state gets reported instantly and super reliably across the entire ship.
Think of this table as the translation dictionary. At the very bottom end, 4 milliamps means a pH of 0. We're talking extremely acidic. All the way at the top, 20 milliamps means a pH of 14, super alkaline. And right there in the middle, that's our sweet spot, our target for pure, neutral water.
So the most important thing to get is that this relationship is perfectly linear. It's a simple, direct scale. As the water's pH goes up and gets more alkaline, the milliamp signal from the transmitter goes up right along with it. It's elegant, and honestly, it's beautifully simple.
And that brings us to the magic number, 12 milliamps. When an engineer sees 12 milliamps on their monitor, they know the water has a pH of 7. It's perfectly neutral, not acidic, not alkaline. That is the number everyone wants to see.
But, things don't always stay perfect, right? So what happens when those numbers start to drift? Well, this is where the system really proves its worth, by sounding the alarm before a small problem can turn into a major disaster.
See, for water produced on a ship, there's a kind of Goldilocks zone. Typically, the pH needs to stay somewhere between 6.5 and 8.5. That range makes sure the water is safe to drink, but also won't damage any of the ship's expensive equipment.
And here is exactly why that zone is so important. If the pH drops too low, the water gets acidic and will literally start to eat away at pipes, tanks, and machinery. But if it goes too high, it becomes alkaline, and you get mineral scale building up, clogging systems, and messing with sensors. Neither one is a situation you want.
So this is basically the cheat sheet for the engine room. As soon as that signal drops to about 11.4 milliamps, which means a pH of 6.5, a low pH alarm is triggered. If it climbs up to 13.7 milliamps, or a pH of 8.5, the high pH alarm goes off. And of course, there are critical alarms for even more extreme values.
So when that alarm sounds, it's a call to action. It signals the exact moment where technology hands the problem over to the human element, the skilled engineers who have to figure out what's wrong and fix it before it gets any worse. And there's absolutely no waiting around. The protocol is crystal clear. If you get an abnormal reading, you investigate it immediately. It's a serious issue and it demands attention right away to protect both the crew and the ship itself.
And this is pretty much what that investigation looks like.
Is the probe itself broken? Has the sensor lost its calibration? Could there be a tiny seawater leak somewhere contaminating the freshwater? Or maybe it's something as simple as electrical interference on the line. The engineer runs through this checklist to find the root cause.
Ultimately, when you boil it all down, that's what this entire system is for. It's not just about knowing the pH. It's about getting that early warning. It's about proactive safety, turning what could be a disaster into just another routine fix.
So this digital watchdog turns an invisible chemical property into a clear electrical signal, all to keep a ship running safely. It kind of makes you wonder, doesn't it? What other invisible things in our cars, our homes, and our cities are being silently translated, just like this, every single second of the day?